Well, welcome everybody. I'd love to introduce Eunah Kim from Cornell, and who's been doing a lot of interesting work on applying machine learning to condensed matter physics and trying to make better models of this phenomenon using the new toolkit. Welcome, Eunah.
All right. Thank you. Thank you, Greg. And thank you for this opportunity. I'm very excited to be presenting. Um, so I want to talk about data-centric learning of quantum matter. And but before I start my talk, I want to briefly advertise the new AI Institute, the NSF AI Institute. These are the PIs who are part of the institute. This is NSF effort to use AI to advance materials discovery, but at the same time allow for the materials challenges to really push the development of new AI algorithms and modalities. And some of the work that I'm going to be presenting is that really inspired the institute, and it's now being driven by the institute. So let me first start by talking about quantum matter as a modeling problem. So what are quantum matter or quantum materials? I use the term quantum matter to include synthetic systems, which could be human designed with a solid state material such as Moray systems or some heterostructures, or it could also include even more synthetic systems where we have either trapped atoms or ions, or used macroscopic quantum states to emulate or simulate many-body state. So to be more inclusive, I use the term quantum matter, but our thinking around quantum matter is really inspired and informed by what we want to understand about quantum materials. So what are quantum materials? Quantum materials are materials whose macroscopic behavior, the behavior that we can hold in our hand and feel, is governed by a many-body quantum state, where relevant objects are object is global and collective, not a single particle. I'm going to make it a little more concrete later. What do I mean by not being a single particle? But to get to the point right away, it really means that you cannot factorize. Small adjustments to an external knob can reorganize the entire state and result in a very different situation. And examples are superconductors, such as high-temperature superconductors, topological materials, and quantum magnets. So to make this a lot of words a little more tangible, I like to use an analogy. So here I'm showing you a picture of a material called YBCO. It's a high-temperature superconductor. And what you can notice is that it looks like a piece of rock. It is a ceramic. So it's really like a piece of rock rather than your familiar wire. Now, when you change the external knob, meaning, for instance, if you change the temperature, at very low temperature or temperatures below the transition temperature, electrons in this system, although we cannot see them, behave at high temperature. Electrons in the system are in this kind of chaotic state. They are bumping into each other all the time. And because it is not a good conductor as a result of all this scattering, what you see when you hold the material at a room temperature with your eye is that it looks dull. The fact that it looks dull is a reflection of the microscopic state where electrons are very much bumping into each other, and it's in a chaotic state. However, if you lower the temperature below the transition temperature, all this collection society of electrons enter a coherent state where they all move in a lockstep, and there is a macroscopic coherence, phase coherence across the entire system. And so when we try to understand the material, we're not trying to only understand some static ultimate answer, but we need to understand what are different possibilities and how easily, quickly can you go from this kind of state to this kind of state when you adjust external knobs. And ultimately, because we have to understand how many quantum mechanical degrees of freedom are collectively exhibiting the property, we need to think about the many-body quantum state. So here I want to attempt a quick sort of primer on quantum many-body physics in 1 minute. I'm going to start timing. Let's see if I can do this in 1 minute. So here what I'm showing is a Schrödinger equation. It is maybe I maybe designed to this equation to look intimidating because that's part of the point. But if you sort of look at just the larger structure, this is a partial derivative in time, so it is about dynamics. It says some object psi who it has time evolution, and its time evolution is dictated by some operator called h hat, that's Hamiltonian. Then what is this object? This object is a quantum state, symbolic representation of quantum state. It's a complex valued vector in exponentially large space. And as the equation states, this is the famous Schrödinger equation for many-body system. This state evolves in time, and it evolves in time according to this operator. It is not sufficient to know one state, not only because it evolves in time, but because in order to understand finite temperature equilibrium property, I showed how the state of YBCO depends on temperature. So you want to be able to access different temperatures. At given temperature, at finite temperature equilibrium state, you need to understand an ensemble of these states. It looks like it's hard enough to know one, hard enough to track one, and I'm saying we need to know an ensemble of them. And often important material properties are out of equilibrium properties, such as transport. So even if I knew the ensemble of these states to know the description of an equilibrium state, it looks like there will be some properties that will be out of reach of predictive framework. So this is what quantum many-body physics is about, and through and through it. Yes.
Okay, so because this seems rather core, I think it looks like the key thing you're showing is that unit ensemble is not for probabilistic phenomena; it's for sensitivity analysis, because this is an ensemble not of sample like measurements; it's an ensemble of wave functions.
Right, ensemble of vectors in this Hilbert space that we need to be able to access. So knowing one is not enough. You need to actually know quite a few of them, possibly very many of them, to be able to actually accurately describe. So I am setting out the problem in a very rigorous manner. So this is a rigorous problem definition. And you can already sense that to do this rigorously sounds hard.
Yeah. And the idea is to get the phase transition behavior. So you say like in one sample of wave functions, one phase, another phase, that kind of stuff.
Something like that. Maybe I'll get to what is it that we would want to model. Okay. So, but first I wanted to set out the problem in the most rigorous, define the problem in the most rigorous sense. And then I want to start talking about how we make progress. If the problem is so hard, how have we been able to make any progress at all? Well, there are these so-called conventional materials for which we know a lot about. Copper, silicon, we know them. Why is it possible that we can know them and with confidence and not be violating the fundamental principles? The reason is that there is some very simplifying thing that can occur that simplifies our problem. But then when we say quantum material as opposed to conventional material, that simplifying assumption, the legality of that simplification will break down. And that's where the challenge enters. So what is it that is simplifying? What is simplifying is, can you factorize? Can you factorize this many-body wave function, which lives in this large dimensional Hilbert space, into smaller bits that you can individually try to understand and then put it back together? So when you can factorize, that is what we call single particle description, and then a problem becomes much more simpler. And when you can factorize, that is properties of conventional materials, very good metal or semiconductors. But quantum materials are the material systems in either in all regimes, or in some specific regime, especially it could be a lower temperature where quantum mechanics is more important. There are situations where we cannot factorize, we cannot use this convenient approximations. Okay, so so maybe we want to model, but what is it that we want to model? What do we want to learn about these? Well, if I want to be like almighty, from almighty's perspective, perhaps you start with this catalog of elements, and you might imagine that, I want to make a material called AXDYEZ. I've carefully chosen the letters that are not in the periodic table. So A represents one element, D represents another, E represents yet another element. This is a 3-element compound. You can imagine 2. You can imagine many more. But I might be curious whether certain element can form. Now you can see that the number of possibilities is also vast because the periodic table is big, and you can imagine arbitrary combinations. But when I imagine an arbitrary combination, that may not even be a great time to kill time. Great way to kill time. But there's a big question mark. The question mark is, I can think of something, it may not form. Most likely it won't. And even if it forms, even if a compound would form into a single crystal, there can be multiple structures. But I might have a desire to be able to model something like that. Probably I might have such a desire because I want to know what kind of property this material can have. And most likely, my desires are driven by wanting to be able to make a material or put it in a condition that has properties that I desire. It could be high K ferroelectric. It could be high temperature superconductor. It could be high temperature magnet, or it could be some other property. But there are properties that I would be interested in. Well, if I know a compound and if I know the structure, that does not put me necessarily all that close to being able to predict the properties. What property a given material exhibit depends on external conditions. It depends on and the various measurements we can perform on the material tend to under constrain. So this is to say that although this being able to go down this kind of program would be something that we would desire, there are clearly challenges in forward modeling. So there are forward modeling challenges. There's exponential state space if I think about my wave function. And if I want to try to even hold it and think of optimizing, there needs to be an aggressive compression. What is in that large space, there may is an underlying manifold that determines interesting properties, but we don't know what that manifold is a priori. The wave function that we might be wanting to represent is not something that we can observe through a measurement directly. We can observe some part of it. We can learn some probability distribution, but we only are allowed to have partial information by the rules of quantum mechanics. Given these kind of challenges, any attempt at modeling requires strong inductive bias. So any kind of forward modeling would come with various bias, and there is always the challenge of whether you have put yourself in a box that is away from the answer that you are after. Okay, so because if the forward modeling is challenging, we would want to start from measurement and observations. That traditionally in condensed matter community, we call it phenomenological approach, that you look at various observations and try to constrain your thinking based on observations. There are many different types of measurements that we can take. Each of the measurements give us only some low dimensional projection of this wave function, if at all, or the collection of the states. So going from this inverse problem of going from these are all the measurements that we've taken, now can I figure out the model, is also a very hard problem. So I want to approach this challenging problem from the data-centric perspective and think of and try to make progress by learning effective representations using AI methodologies. Given that my mission is not predict one thing or try to solve one nonlinear equation, but trying to be predictive and knowledgeable or insightful about fundamentally multifaceted problem, this approach of trying to make progress would have to be strategic and case dependent. So what are the difficult data problems in quantum matter research? One type of data-centric problem is big data in high dimension. I've already talked about how the wave function or the quantum state, if you have a mixed state, you have a density matrix, it lives in a high dimensional state. That's what the system is residing in. But there is a limitation in our knowledge, like how we can access. We only access through limited projective measurements. Another type of big data in high dimension is large volumes of data that is now enabled for detection and storage by the developments in various measurement facilities. So large data, larger than what we are traditionally used to modeling, or fundamentally trying to go after the quantum state in a large dimensional space. These present problems in high dimensions. And we are lacking a traditional tool to go after these models, and forward modeling is very limited. Another type of data problem is the heterogeneous accumulated knowledge, the empirical drive, trying to make progress by collecting various results of experiments is a very natural sort of a scientist approach, very natural scientist approach. But for long-standing problems, there have been efforts by the community to do various experiments, and the results have been documented. But those are kind of scattered across literature in various databases, and how to learn from the humanities effort thus far. Superconductivity research has been ongoing for 100 years. So how can we learn from 100 years effort by the humanity? That's another kind of data challenge. What I want to talk about is various efforts from my group through collaboration with many collaborators in trying to bridge the gap through, let's call it representation learning. So I want to talk about first quantum attention network for state characterization, where we tokenize a set of snapshots. These are 0 and 1 projective measurements on quantum hardware, quantum simulator. But we've tokenized the whole collection of them as a set batches to learn the representation that captures high moment and long range correlations. Another thing that I want to talk about is X-ray temperature clustering, temperature series clustering for X-ray diffraction. We call it X-TEC. X-TEC treats temperature series of X-ray intensity as a point in high dimensional space. Once you decide that, oh, I want to treat this as a point in high dimensional space, when that makes sense, then you can bring in various clustering algorithms to in unsupervised way discover different kind of physics that's ongoing in different space in this reciprocal space. Finally, I want to talk about something that I'm very excited about, which is getting me closest to that original desire to be like the designer of the world, where we want to be predictive in designing or understanding superconductors. That's Gaussian process TC predictor. Okay, let me start with the complex quantum state. Having many quantum degrees of freedom, or say many qubits or spins, does not necessarily guarantee you're going to have a complicated state. You can have everybody just pointing a zero, and in this fiduciary state of everybody pointing zero at a product state, no matter how many times you measure, if you prepare the same state, you will always measure 0, 0, 0 with certainty, absolute certainty of probability 1. And that's a very simple state. What is a complex state? Complex state uses up that entire space that is possible, the entire Hilbert space. And it does so. What I'm presenting here, showing here, is a probability of measuring a particular measurement outcome. Each time you measure, you're going to get a different outcome. One time you're going to get this outcome, another time you're going to get this outcome. The reason you're getting different outcome each time you measure is because the system is in a massive superposition. And when it is in a massive superposition, and when every degree of freedom are entangled, then you are really exhausting this exponentially large space. And that is what a complex state would look like. So the complex quantum state is kind of like two-faced, like a two-faced god Janus. It's got the aspect that, well, when you can represent this many possibilities by preparing one state, there must be some advantage in using such a formalism. At least this would be a way to understand and represent highly entangled quantum state in a way that is more native than trying to represent it on a classical computer. And more broadly, this might be a promising way to go after classically hard problems. However, another phase of complex state is that it's challenging to read out. Each of these outcomes occur probabilistically. So when you have a complex state whose probability distribution is so spread out, it means you need to take many measurements. So the large sample complexity and the hard inverse problem is what's going to make making use of these complex states challenging. So here in this paper, with this group of collaborators, especially driven by my student Eunah Kim, former postdoc Yi-Ching Zhou, and the current former student Yi-Ching Zhou, now at Google Quantum AI, and former postdoc Yi-Chen Shu, current postdoc Yi-Chen Shu, I'm mixing up people. We have collaborated with experimentalists and also my colleagues in computer science, who are now part of AMY, to make progress in learning the complex quantum state. And what we thought of is, okay, this is a hard problem. Exponentials are scary things. This curse of dimensionality is very real when you try to work with complex states. So if you are facing a very difficult problem that is intrinsically sample greedy of the data and sample, and your experimentalist can only give you finite amount of sample, You want to find the most promising, most easiest, lowest lying fruit, lowest hanging fruit that will nevertheless tell you something very useful. That will be my optimization strategy. So what we thought to do is to formulate problems as a classification problem. Classification problems are far more forgiving to smaller volume of sample compared to trying to be generative. Here are three problems that we thought of, and one is trying to distinguish whether a state is in a volume law entangled state or in a area law entangled state. Another is trying to assess whether my state is in a topological state, which is a situation where you can use a many-body topological state to encode a logical information in a redundant way. So it's a scheme for doing fault-tolerant quantum computation. But if the state is experiencing too much noise, it will not be topological and it cannot encode logical information. That will be a trivial state. And more fundamentally, addressing the complexity on its head, you can ask, when you have a circuit that is designed as you go in depth to entangle more and more, can you tell, given the sample, whether the state was from a relatively shallow circuit or a deeper circuit? If I have the full knowledge, the probability distribution associated with different bit strings would be different between these two. This is actually obtained from classical simulation emulator for the quantum system. But I'm given a task of having to learn the difference or existence of difference, distinguishing with a finite volume of sample. So what we thought to do in trying to approach this hard problem was to realize, well, it's hard to tell with naked eye that this is different from this. This is actual sample count. This is made from actual sample count, although underlying distributions are different. It's about the limitation in the sample complexity. But if there is a distinction, it would be in the moments of the distribution of this outcomes. So we thought of how to learn high moments of this distribution, and we thought to use attention mechanism in a way that respects the structure in the data, symmetry in the data. So we tokenized entire snapshot, and we moreover actually work with a collection, a batch of this bit strings. Each of these are bit strings. So one of these will be in that B axis. Red is let's say up, and empty circle is down. The way we designed the architecture was that we were very much guided by where we have knowledge, theoretical knowledge to suspect meaningful information is present, and trying to make sure we respect the known symmetries in the data. That because symmetry allows one to sort of reduce how much you have to study. And the symmetry in this case was that if I am to treat each of the snapshots as a token, I have to recognize that there is nothing particularly meaningful about the order in which the samples occur. So we wanted to ensure that there is permutation invariance. So this architecture we put together was designed to try to start capturing changes in the correlation or the moment by our attention encoder looking at a batch of snapshots at a time, recognizing that each of the snapshots should be taken in a permutational invariant way. And this set self-attention was further economized from the computing perspective by introducing what we call miniset. And then we collapse it back through this sort of decoder layer, where we have another opportunity, the architecture has opportunity to learn which of this data is more informative for its learning task. And then there is an output, and we've formulated all the problems as a binary classification problem. And this design, from the design, we can back out that our architecture would in principle have access to very high moments. It's not calculating the moments because its set size is limited, but it will have approximate access to the moments. So how well did this work when we try to compare shallow depth and the deep depth? When we don't take the permutation invariance into account in these MLP or CNN or vanilla transformer, these are algorithms that we have benchmarked against. We're getting 50% accuracy, which is really nothing. But with the QuAN architecture, quantum attention network, that is respecting the permutation invariance and using the set structure, we were able to, and this 50 is denoting how large a moment it can access, we were able to get relatively high accuracy in this classification problem. Now, another thing we were able to do was to train the model with the classically simulated data that is simulated on a classical computer, comparing to the sort of a forward modeled benchmark of cross entropy, where you compare the data to your forward model. That cross entropy benchmark essentially stops being able to distinguish depth A from depth 20, which is what we use as a reference point. But QuAN can extend its knowledge of shallow state up to 10. So this is seeing that, well, depth 8 is shallower than depth 12, where here you cannot see that depth 8 is shallower than depth 12. When we then use the experimental data, when you try to compare experimental data to forward model, classically simulated forward model using cross entropy benchmark, you can not really tell anything is happening at any depth, because the data is now very much ridden with noise. So when you try to compare the experimental data ridden with noise with limited forward model, because our forward model tends to be limited with our inductive bias about a perfect system, it's hard to model a non-perfect system. So this is not showing any change in the depth, but when we use use QuAN that was trained on simulated data, even with the noisy experimental data, it was able to find features in the data that really resembles the change in the complexity in the perfect data. So the fact that we were able to see similar kind of change in distinction between shallow state and a deep state, and recognize these lower depths as a shallow state, was really encouraging as a way of giving us the insight that this architecture was able to learn the complexity of this state in a way that is meaningful and that's transferable to real world data. And this is one example case, but what we've shown in this paper was that this approach is actually broadly for all the 3 tasks that we have tested. Repeatedly, we found that this approach of trying to learn the complexity of quantum state by thoughtfully designing what is it that we want to learn into our architecture and how we feed data in what structure can allow one to learn complexity of these quantum states.
So question,
Question?
what
Yeah.
what kind of features is it picking up? I mean, because I'm thinking if this was a classical circuit, the related problem would be more like you take random samples of a graph and you figure out the complexity of a graph from its random samples. This is nastier. It's
Mhm.
random samples of nodes of the graph, and if they're correlated, you kind of get a complexity metric. Is that the kind of feature this thing is picking up, or something else?
So what we were able to with the this random circuit, the best we know is that um, accessing high moment was useful, and there is a rigorous theoretical understanding that as you make this circuits deeper, is a very high depth limit, which is what's called hard random. And what is known is that as you increase the depth, you at the lower depth, you would still resemble the hard random in low moments, but you will resemble hard distribution in the moments only up to certain high moment. So learning moments we knew is a good strategy for this very structureless data, and that knowledge was at the core of our design principle, that we wanted to learn moments in a most efficient way, and we don't try to model the moment rigorously because that's going to be just too expensive, but we try to learn, okay, the moments are changing, that signaling, that is kind of low bar to clear because we're trying to solve hard problems and we want to make progress by defining what is a low bar that is nevertheless meaningful to clear. Does that answer your question?
Yeah, that helps a lot. Thank you.
Okay, so now I want to switch gear and switch it to a different problem. Now this is much more close to like solid state. Previous one was motivated by quantum many-body physics, but physical system was quantum simulator. X-TEC is a versatile, unsupervised machine learning approach for evolving high-dimensional data. And you can find more about this in this first paper where we introduced this. And now we've been also making discoveries using X-TEC. This was, again, collaboration with my co-director of AME, Kilian Weinberger, and now colleagues at Argonne National Lab, and my colleague at Cornell High Energy Synchrotron Source, Jacob. My colleagues who are on the ground doing the measurements were extremely helpful. Helpful is an understatement. They defined the problem, they brought the problem to us, but we really brainstormed together to decide what will be a meaningful thing to learn. So what are we dealing with here? Imagine a single crystal, strontium rhodium tin, which is now being measured. And what you're seeing here is that as you change the temperature from high temperature to low temperature, this is a visualization of X-ray intensity in HKL or momentum space, reciprocal space, XYZ, reciprocal space. And what you can notice is that, intensity is increasing. So something is changing. This is an example of how our measurements change. Now, this was a terabyte, several terabytes of data, close to 2 terabytes, I believe. And traditional approach wouldn't be looking at this exhaustively. That's not possible. So traditionally, although the measurements have this big volume, one would look at some, you would pick out some regions to study and study it manually. You give this data to X-TEC. X-TEC will sort in this whole reciprocal space into our momentum reciprocal space points, which are behaving one way, and other points that are behaving differently. It's a clustering algorithm, and it's clustering based on temperature evolution. Now, that comes to us, scientists, and then we can look at it and say, actually, these are related to this emergent phenomena called charge density wave. And this is sort of a background. So how do we do this? the first starting point was to decide, oh, let's treat the temperature-dependent intensities as a point in high-dimensional space, and each point is associated with each reciprocal space position. So at a given reciprocal space position, here, if I pick a coordinate, intensity is changing as a function of temperature. So each of the measurements all put together, we represent that reciprocal space as a point in high dimensional space associated with all these different temperature measurements. That is, entire trajectory is treated as a point in the high dimensional space. And you can see why this could work. This is an example of the raw data, intensity as a function of temperature, plotted for many different positions. And you can see that there is one group behaving this way, another group behaving this way, and then there is maybe background. I picked something that is easy to see by eye. Now, if I pick 2 points in temperature, now that's a 2-dimensional space as far as the temperature is concerned, and you can see the clustering emerging. So this was, as far as the algorithm goes, our X-TEC 1.0 was a very simple Gaussian mixture model. Anything even simpler didn't quite work because we need to be able to cluster in an anisotropic way. But Gaussian mixture model was very quick, and it gives you what you can believe. There is no black box about this, but it gives us a very rapid turnaround in going from the measurements to an understanding. And we were able to use this approach to discover Bragg glass phase and palladium intercalated erbium tritelluride, which was published in this work. The bottom line is, by using X-TEC, which allowed us to examine not just one Brillouin zone, but all of the Brillouin zones and make an observation that is collective across all the Brillouin zones, allowed us to figure out the noise or the broadening that is, or the fluctuation that is momentum independent. And by tracking that, we were able to discover Bragg glass. This was in collaboration with Ian Fisher and his group. Now, what really excites me is the fact that this algorithm is being built into the user interface at Advanced Photon Source and also at Cornell High Energy Synchrotron Source, which will allow the users, students coming to do their beamline experiments to make their adjustments and make their explorations real time, instead of doing the measurements, going back home, and later finding that they should have done a different measurement. And we made it all sort of user-friendly with a graphical user interface without necessarily having to know what they're doing. They can take data, feed it to the X-TEC, and decide, oh, I want to really zoom into this temperature range. So that's an example of thinking about the problem statement and really thinking from the data-centric perspective. If I want to look at this as a data problem, what kind of data problem is it? And then deciding what is the most economical algorithm to approach. Now we are finding this approach to be really helpful in also analyzing 4D STEM data. This is in collaboration with Judy, where we can detect different regions to exhibit different charge density wave transitions by analyzing the STEM data. So now in remaining 16 minutes, I want to move on to the third topic of dealing with community's effort. Up until now, I've been working with, I would list all my collaborators. My collaborators were those who did the experiment and brought the data problem to the table. Now I want to talk about the data problem the community has brought to the table over generations of research. So superconductivity was discovered almost 100 years ago. We know somewhat about superconductivity. There are things that we know about superconductivity, but our knowledge is very, very limited. However, there is a lot of research that's been done, and and this group of people in Japan have put in heroic effort to collect various known facts, numerical facts or known facts based on the literature. So each of these entries in the superconducting database is associated with literature, and you can trace back who said what about based on what measurement about a given material. So being able to start working, trying to stand on the shoulder of not one giant, but whole community's effort is an unprecedented opportunity that this generation has. And we want to try to see whether we can use that for our advantage. What is it that I want to do? I said, I want to go from periodic table, propose a material, and propose its property. Now that's very hard. Because it is hard, looks almost impossible. There are many steps that we just simply don't have a formalism to go brute force forward. So I want to resort to empirical approach. Why would that be even sensible? Well, there is a precedent. The precedent is Mendeleev himself. Mendeleev imagined the latent structure in the space of elements without knowing quantum mechanics, without having access to quantum mechanics, based on the observations by discovering patterns. So periodic table, as we know, is a great, it tells us a lot about the elemental materials. Questions, can we do something about non-elemental materials? And this is where you can find more about this work. And this was done in collaboration with my student, Yanjun Liu, postdoc only lesser, former postdoc Krishna, current postdoc Aditya, and in collaboration with Leslie and Jacob and his student Natalie. So there were earlier works. This database has now been around for a while. Various efforts to use the standardized data, and most of the time, the efforts were using the chemical formula, thinking of the periodic table as a palette, and think of each of the element as one possibility in that vector. The problem is, well, as we know, that chemical formula for pencil lead and chemical formula for diamond in a diamond ring are the same. It's just C, carbon, but their properties are enormously different. Partly due, probably largely due to the fact that their structures are different. So structure is clearly very important. How do we take structure into account when in our space of materials, some materials are elemental, some materials have 2 elements, some materials has 4, 5, 6 elements. How do we come up with a scheme that can reflect chemically meaningful information? So what we decided to do was to build out graphlets systematically. So this is once again thinking about what is the sort of raw elements or representations that we believe has reason to be useful, chemistry driven. So here our graphlets, these first order graphlets are properties of individual elements, and second order is 2 element pairs, and third order will be 3 element pair. And for each of these orders, we are looking at elemental features that chemists tend to pay attention to, plus structural aspects. Structure enters through which atoms are neighboring and what is the length of the bond. So once you have neighbors, you start to ask, oh, how close or different are their elemental properties, which is going to start capturing properties of the bonds. So the design principle was to be very frugal with the information that we demand, because when you try to ask, okay, give me the full DFT band structure, to produce such data is a lot of effort, but moreover, it is not very reliable. We wanted to use everything that is measured and derived from experimental observations. Well, then comes the question that, this is one material, this is another material, they have different number of atoms, different number of elements. How do we come up with a unified scheme? That's when we came to the idea of histograms. We said, okay, we're going to treat each of the material as a histogram of these graphlets. And then we realized that these histograms are capturing some of the information that have been previously ad hoc, manually recognized as meaningful. For instance, for cuprate copper oxide-based ITC superconductors, there have always been an observation. There is the distance between these oxygens and the plane are important. Now, when we just look at all our second order features, which are interatomic distances, what was deemed important as apical oxygen distance now is information that is captured in here, but it's going to be more systematic and more comprehensive. It's an information. The interatomic distance is something that can be applied across different families, as opposed to apical oxygen distance, which only applies to cuprates. So until now, empirical studies, phenomenology was manually done, looking at what we can hold in our heads, what we can hold in our paper, and categorizing in our heads. Now we can approach this in a more systematic and at scale, and that's what we've done. We also took the crystal symmetry into account, and we approached this problem with two algorithms structure. One is to use Gaussian process so that we can learn uncertainties. TC of a given material can depend a lot on how pure the material is, and we were hoping that by knowing uncertainties, we can capture some of those. And we've also tried as a benchmark simple neural network. We took the data from SuperCon, which has all these superconductors and their TCs, transition temperatures, and their measure structure information in ICSD. And then we do like 80-20 split to train on the part of the data and test on the remaining part. In the interest of time, I'm going to skip the description of Gaussian process, except that we were able to use the histograms as feature by coming up with a new kernel that uses Earth mover distance as a measure that measures the distance between the histograms as features, which was essential for us to make progress in wanting to use this histograms as features. So here is the result. Our Gaussian process TC predictor GPTc is showing R2 score of 0.93, 0.94, which is quite good. But most interesting thing, one of the very interesting thing about our predictor is the uncertainty estimate. Now, that uncertainty estimate comes to really shine when we ask, okay, so this was all done on the known superconductors or known up to a given date. Every database has its timestamp. So one test on GPTc's capability would be to ask, what about superconductors that were since discovered that was not in the database? And that test was done for what's called nicolates. And we found that GPTc predicts the nicolate transition temperature, even including the uncertainty from sample to sample, with captured through uncertainty. And that really encouraged us to try to pursue synthesis. Can we try to use this model to predict superconductivity on material that has yet to be tested for superconductivity, and see can we nail it? So I'm in the interest of time, I'm not going to go into how we were able to reduce the number of features to just 4 and find that gain new insight and benchmark, and also we can classify. But actually, I'm going to go back to one slide, kind of ran out of time in preparation, which has something very exciting. Early on, I think I moved fast, so it wouldn't have. I'm sorry. Where? Okay, here. Oh no, did I not add that? Oh, I think I failed to. Did I? Oh, right. I think I didn't. Let me just quickly. Oh, well, so just the, let me see if I can change the, give me just a second. Gonna change which screen I share so that I can show.
Yeah, it's the upper button. Yeah, you should be able to do it.
Yep. Let's see. Got it here. So here, what I'm showing is, this is experimental data. This is a material, platinum lead bismuth, PT PB3BI. This is not in the archive version yet. So I'm giving you a sort of a scoop. This material has never been reported as a superconductor. We gave this material, we ran all the materials in the ICSD that is not yet reported to be a superconductor through our GPTc predictor. And this came out, this material was predicted to be a superconductor with the GPTc prediction of transition temperature of 2.93 Kelvin with some uncertainty. And my colleague, collaborator, Leslie, was able to quickly synthesize the material because it is a material whose structure was already known and material that is known to form. Just it had not been tested for superconductivity. So she synthesized the material. Here is a picture of the crystal. And then they measured. Here you can see that the from the susceptibility measurement, zero field cooled susceptibility measurement, identified TC is 2.98 Kelvin. GPTc prediction was 2.93. It didn't involve calculations. It just required chemical formula and a structure. What I'm really excited about is what we can do going forward with this, which is we believe, now this is actually not a matter of belief, actually I know as a fact that I can do this. First of all, when our predictions can be tested, we have colleagues synthesizing a bunch of superconductors that we have predicted. When we discover new superconductors this way, that information from those measurements can enter into training GPTc. It's relatively fast, and as more materials are found, it can enter into GPTc and it can improve the model. But also, if the predicted TC in this one case, we were very, it worked out really nicely. But my R2 score wasn't 100. It wasn't 1. It was 0.94. I'm sure we will find cases where the observation is out of distribution, but it can be fed into the model to improve the model. But moreover, something that's very easy to do is, because we are not using whole spectrum or wave function or band structure as an input, just the structural information and the chemical formula. If we have a reason to believe structure can be altered, for instance, by straining, by putting pressure, we can tweak that and see how the predictions change. So I believe I'm really excited about this GPTc now becoming something that can allow fast exploration with experiments and chemists, material scientists, theorists, and modeler all in the same loop. With that, I'm out of time. Let me summarize. I've talked about essentially why we want to take data-centric approach. But if you want to take data-centric approach, how can you make progress on this multifaceted problem of understanding learning quantum matter? I talked about using attention mechanism in a sort of a strategic way, respecting the symmetry and structure of the data to learn complex quantum states using QuAN. I talked about X-TEC, clustering in reciprocal space for unsupervised discovery of new ordering phenomena in X-ray diffraction or even glassy physics. And finally, I talked about using supervised machine learning to learn to predict material properties, specifically superconductivity and transition temperature. With that, thank you for your attention.
Well, yeah, thank you very much. This is fascinating stuff. Well, have a great day. Thank you for sharing your time.
All right. Thank you. Bye.